Today, it's our pleasure to listen to Maxime Ingremau, who is going to talk to us about how Lagrangian states evolve into random waves. As usual, don't hesitate to ask questions during the talks. If you ask them in the chat, we will share them with the speaker. And well, Maxime, the floor is yours.
Okay, thank you very much, Laura, for the invitation, and thank you for the introduction. So indeed, I will talk about Lagrangian states evolving into random waves. So this is work in progress with Martin Vogel and joint work with Alejandro Rivera, and it's work about related to Berry's conjecture. So the initial version of Berry's conjecture is about eigenfunctions of the Laplacian, and so I will give a rather long introduction about eigenfunctions of the Laplacian. So the framework is the following. We'll be working on a smooth Riemannian manifold, connected, compact. And so, as you all know, there exists an orthonormal basis of L2 made of eigenfunctions of the Laplacian. So I will denote by lambda n the eigenvalues, and phi n the eigenfunctions. I will order the eigenvalues. I will be interested in the behavior of the eigenfunctions phi n as n goes to infinity. So that's what's called the semiclassical limit. And these properties depend a lot on the properties of the geodesic flow on your manifold. And so in particular, in quantum chaos, we are interested in the properties of these eigenvalues and eigenfunctions in the semiclassical limits on manifolds where the geodesic flow is chaotic. And the most important example of this is when your manifold has negative sectional curvature. And there is a very famous theorem in quantum chaos, which is the quantum ergodicity theorem. So it is due to Schnirelmann, Zeldich, and Conan-Verdière. So, well, maybe some of you don't know, Steve Zeldich passed away yesterday, and so this talk is dedicated to his memory. And so this quantum ergodicity theorem, which was very influential in the community, says that if you take your eigenfunctions squared and you put a dx in front of them, so it gives you a sequence of probability measure on your manifold, and it converges weakly to the uniform measure on your manifold. So in other words, if you integrate any function against the squared eigenfunctions, then it will just converge to the average value of your function. So there is, so actually this is not completely true. This holds only for a subsequence of density 1 of eigenvalues. So that's the bad news. And the good news is that there is a more general version of this theorem where you have equidistribution not only on the manifold, but in phase space on the cotangent bundle. And this uses the language of pseudo-differential operators, but I'm not going to talk about this today. And so, as I told you, you have to extract a subsequence of density 1, and there is a central conjecture in quantum chaos, which is the quantum unique ergodicity conjecture. And conjecture is that on manifolds of negative curvature, you should not need to extract a subsequence in this theorem. So this is a very hard conjecture. There were some advances by Anantaraman, Nonnenmacher, and more recently by Dyatlov, Jean, and Nonnenmacher. But this is not the conjecture I want to talk about today. I want to talk about another conjecture, even harder somehow, which is Berry's conjecture. And Berry's conjecture says that your eigenfunctions on manifolds of negative curvature should behave like Gaussian random variables somehow. So there are several versions of this conjecture, and I will try to explain all of them. So the first version, which is already super hard, but it's a baby's version of Berry's conjecture, says the following thing. So imagine you choose a point at random, uniformly at random on your manifold, and you look at the evaluation of your function at this point. So this gives you a random variable, a sequence of random variable. And so the conjecture is that this sequence of random variables should converge in distribution. They should converge weakly to a Gaussian variable, a standard, correctly normalized Gaussian variable. And so this would almost imply the quantum unique ergodicity conjecture. And this conjecture is well, already out of reach. But still, I will focus on a more complicated version of the conjecture, where you study more complicated information about the eigenfunctions than just its value at a point. And as a motivation for this conjecture, let me show you a picture which I took from a paper of two physicists, Vogel and Schmidt. And so it represents two eigenfunctions. So on the left, you see an eigenfunction of the Laplacian in a billiard where you have a chaotic dynamics. So it's not exactly chaotic. It's not exactly a negatively curved curvature, but it's chaotic enough. And so that's what you get. And on the right, we have a random eigenfunction of the Laplacian on the plane. And so what you see, even though it's not very rigorous, is that the two pictures are extremely similar. And so Berry's conjecture, very informally, says that the two pictures you have are basically the same. So now what I would like to do in the rest of the introduction is first explain to you more what is the picture on the right, and then why is it similar to the picture on the left? At least what does it mean to have similar pictures? And yes, sorry, I forgot to say something important. When I say that these are pictures of eigenfunctions, of course, no, these are pictures of their nodal domains. So that means that in white, you have the places where the function is positive, and in black, where it is negative. So that's the information about the eigenfunctions, which is pictured. All right, so let me explain what are these random eigenfunctions. So since we're talking about probabilities, we need a little bit of probability vocabulary. And so a random field, it is a probability measure on the set of functions on Rd. And in the talk, they will always be smooth functions. So in other words, a random field is just a way of picking a smooth function at random. And we will need a convergence of random fields. So we say that a sequence of random fields converges in distribution if the average value of any continuous functional converges. And here, by continuous functionals, so I mean continuous bounded functionals, sorry. So these are maps from C infinity to R. And C infinity of Rd is equipped with the topology of convergence, all derivatives over compact sets. So somehow it's a local topology. So now I would like to give a few examples of functionals which can be of interest. So for example, you could look at the value of your function, or the absolute value of your function at the origin. And since you need something which is bounded, you must truncate it, but that's just a technical point. So this would be related to the L infinity norm of your eigenfunctions, if you want. Another functional could be an indicator function, saying if your function takes value between A and B when you evaluate it at 0. Or you could take the LP norm in some ball. Or you could look at the length of the nodal set in some ball, or look at the number of nodal domains of your eigenfunction in some ball. So you could really take any functional, all the functionals of interest in spectral geometry can be described in this kind of convergence. And so, how do you define your random eigenfunctions on Rd? Well, as follows. You take a sum of plane waves. So our plane waves will have directions of propagations which will be uniform on the sphere. They will have phases which are uniform between 0 and 2 pi. And the eigenvalue, the wavelength, so you can think of it as being always equal to 1. That's the monochromatic case, if you want. But in some part of the talk, I will also want to consider the case where the eigenvalues are not all the same, but they follow some random, there are random variables following a low mu on 0 plus infinity. And so this is a random field, okay? It's a way of choosing a function at random. And if you divide by square root of n, thanks to the central limit theorem, this will converge for all values of x. This will converge distribution. And so you get a limit, which is a random field. It's called the Berry field. So it's isotropic. That's because the directions are uniform on the sphere. It's stationary. This means that it's invariant by translation in x. And this is related to the fact that the faces phi are uniform. It's Gaussian. That's because of the central limit theorem. And it's monochromatic, where when mu is just a Dirac mass and the lambdas are all the same. And so the picture you have on the right is a realization of the nodal set of the real part of the Berry field, the monochromatic Berry field. You may be thinking, okay, I just showed you one realization of this random object, but it doesn't tell us much. I mean, you cannot describe a random object by just one of its realizations. Well, actually, yes, you can, because the translations act in an ergodic way on this probability measure, on this random function. And it means that all realizations will look more or less the same. I mean, if you look at different parts of the picture and you look in a neighborhood of the different parts, you will recover all the statistics just by moving your look all over the picture. So that explains what's the picture on the right. Now,
what is a mu on the picture on the right?
It's a Dirac at 1. Okay, it's the monochromatic.
Thank you.
Thanks for the question. And so on the left, well, we have a picture of an eigenfunction, and I need to explain to you what it means that they are that the two pictures are similar. And so the general idea for this is to take an eigenfunction and rescale it around at scale h, so around the point x. So look at psi h of x plus hy, and see this as a function of y. So this oscillates at scale 1, okay? And then you take the point x at random. So this gives you a random function oscillating at scale 1. And so that's what we are going to do. But since in most of the talk, I want to discuss the case of manifolds, we need a bit more technicalities. So we are just going to work in some open set where you can define an orthonormal frame. And so instead of writing psi h of x plus hy, you need to use the exponential map at the point x and your orthonormal frame. And so doing this, you do get a random function on Rg, which oscillates at scale 1, and which depends on this parameter x, which you think of as being random. Okay, so our function psi hx, as I just said, with x taken uniformly at random in some open set, gives you a random field. Now you can guess what Berry's conjecture is, or what an interpretation of it is that if you take a manifold of negative curvature and you take an orthonormal basis of eigenfunctions of the Laplacian, then these random fields induced by the eigenfunctions should converge in distribution to the Berry field. Again, if you had this, this would explain why the two pictures here are very similar. Why the nodal length in any small ball will be the same on average here and here. Why the number of nodal domains correspond to each other. This would explain all this. So this is the latest interpretation of Berry's conjecture, but Berry's conjecture has quite a long history. So it was first formulated by Berry in the late 70s in a rather informal way. And then, physicists way say, and then in the 80s and 90s, there was a lot of debate between the mathematicians to understand what was the correct interpretation of Berry's conjecture. And in particular, there were numerical simulations by Schur and Rachner, and there were interpretations of the conjecture by Sarnak and Zeldich. So Sarnak's interpretations were closer to the first version of the conjecture, and Zeldich's interpretations were closer to the second. Somehow he had a more modern point of view, at least that's what I believe. And then people kind of stopped thinking about Berry's conjecture for decades, and it came back to fashion in the late 2000s when Bogomolny, Schmidt, Nazarov-Sodin, and Gaillet-Velchanger worked on these random nodal set of random eigenfunctions, and they were able to evaluate the number of nodal components. And so there was a lot of interest on Berry's conjecture again, and the interpretation of Berry's conjecture, which I presented, was due to myself and to Albert Bergeron and Lemasson in the years 2017, 2018. So the two teams worked completely independently, and we reached the very same formulation of Berry's conjecture. So probably means that it's a reasonable conjecture, or at least it's the most fashionable one today. And then Berry's conjecture was proved, so not in negative curvature, but for eigenfunctions on the torus, the two-dimensional square torus, for some generic families of eigenfunctions. So this was the work of Bourgain first, and then it was generalized by Buckley and Wigman, and improved by Wigman, Yesha, and Sartori. And well, I only related what they did to a more general form of Berry's conjecture. And there is also recent work of Romagnegar, Sartori about families of functions on IRD which satisfy asymptotically Berry's conjecture. So, so that's all I wanted to say about eigenfunctions. And I gave you many conjectures which are extremely hard to solve, and I have no ideas of how to solve them. But well, physicists are not happy with these conjectures. They want even more. And generally, when they speak of Berry's conjecture, it's not only something about eigenfunctions, but also something about propagation by the Schrödinger equation. And to formulate their insight in a rather vague way, so imagine that you're on a manifold or in a domain with a chaotic classical dynamics, and you take an initial condition which is localized in some energy layer around 1, say, so not necessarily an eigenfunction. It could be a combination, linear combination of eigenfunctions, and you propagate, and it should be somehow generic, and you propagate it for some large enough time by the Schrödinger equation, and then it should satisfy the conclusions of Berry's conjecture in the limit h goes to 0. So here h is the semiclassical parameter which goes to 0, And you should think of it as 1 over the square root of the eigenvalue in my introduction. So this conjecture is quite vague, but it is something which is observed experimentally and which is really used in applications. For example, in chaotic electromagnetic reverberation chambers. So this is a picture of the one we have in Nice. We are very proud of it. And so basically what the physicists do is that they just send a wave in a box like this. They send a plane wave, and they have it bounce all over many times. And in the long time limits, what they get is really a random field, a random Gaussian field. So just like in Berry's conjecture. So I will be interested in this talk in this kind of conjectures, but for a very specific kind of initial data. And namely, we're going to work with Lagrangian states or Lagrangian distributions, if you want. So these are functions which are of the following form. It's an amplitude, b of x, times exponential I over h times a phase phi of x. So these are not eigenfunctions of Laplacian in general. They are much simpler. You can think of them as generalizations of plane waves. Okay, if you are on a manifold, for instance, you have no plane waves, but you still have functions like this. And so we say that these functions are monochromatic if phi has a gradient of norm 1 everywhere. And in this case, your Lagrangian states are not eigenfunctions, but they are quasimodes. They are not too far from being eigenfunctions. Okay, and they are associated, these eigenfunctions are associated to a Lagrangian manifold, which is just the graph of the function like this. Okay, it will play a role in the, just the graph of the gradient of the phase, and it will play a role in the sequel. So actually, we're not going to work with all possible Lagrangian states, but only with generic Lagrangian states. And to have genericity, I will need to introduce the space of Lagrangian states, or the space of faces, because it's going to be a generic condition on faces. So what I will denote by z lambda 1, lambda 2, omega, it's just the space of faces whose gradient has a norm between lambda 1 and lambda 2. And this is a very nice metric space. It's if you want, it's an open set in the space of C-infinity functions. And we will also be interested in monochromatic faces. So those which have a gradient of norm always equal to some constant lambda 1. And this is not a nice metric space, because if you perturb a face which has a constant gradient, it's not clear how you can do it to keep a constant gradient, with constant norm. But so if you want to induce a nice metric on this kind of spaces, you want actually to restrict your faces on a hypersurface and then propagate your information in some neighborhood. But I don't want to enter into this kind of details. So in the rest of the talk, I will pretend that this is a nice metric space. And so we will want to talk a bit about dynamics, okay, to understand the relationship with the dynamics. And so since we are going to work on manifolds of negative curvature, the dynamics of the geodesic flow on the cotangent bundle is going to be chaotic. And it means that around any point in the cotangent space, you will have stable directions and unstable directions. And stable directions will correspond to points which will approach each other in the future. And so what we want is that our the Lagrangian states we consider should be associated to faces whose to Lagrangian manifolds. Okay, so the gradient of the faces like this should be transverse to the stable directions. And so what this means in practice is that if you look at this at the graph of your of the gradient of the face, and you take 2 points on this graph and you evolve it by the geodesic flow. Well, the points shouldn't approach each other. They should tend to diverge in the future. And so I will add a little TSD to say that your functions, your phase is transverse to the stable directions in this sense. So there is a very nice result by Roman Schubert, which is an analog of quantum unique ergodicity for propagation of Lagrangian states. So it tells you the following thing. You work on a compact Riemannian manifold of negative sectional curvature, and you consider Lagrangian states, so b exponential I over h phi, and you ask that the phase is transverse to the stable directions. And so you propagate your Lagrangian states up to a time, during a long time, and then you have an analog of quantum unique ergodicity. Namely, you get a function, and if you integrate, you put it to the square, and you integrate it against any function, then this is going to converge to the average of your function A. And of course, there's a normalization factor before, which corresponds to the, it should be squared, by the way, and it corresponds to the mass of your function here. And so there is a restriction on time. It should go to infinity as h goes to 0, but not too fast. It must be smaller than a constant times log h. And so in quantum chaos, this is what's called Ehrenfest time. Okay, the constant which is here is very explicit. It depends on the classical dynamics. And this Ehrenfest time more or less the time until which classical and quantum dynamics correspond to each other. So this is an analog of quantum unique ergodicity. And now I would like to discuss analogs of Berry's conjecture for these propagated Lagrangian states. So the result is more technical, and somehow it's less satisfactory than Roman's result, but still. So it's a result with Alejandro Rivera, and it says the following thing. So we cannot take all Lagrangian states. We need to consider generic ones. So we need phases. Sorry. So the result says that there exists a dense subset, an open dense, a generic subset of the space of phases which are transverse to the stable directions. Okay, it's a G delta dense subset, such that for all such phases we have the following results. So we consider a Lagrangian state with a phases which is generic like this, and we propagate it by the Schrödinger operator up to some time t, and so it gives us a function, and depending on t and h, and so we can so it induces a random field, just like what I said about how you can define Berry's conjecture for eigenfunctions. So this random field, I denote it by FHU of t. Okay, so it is obtained by taking a point at random in U and rescaling your function at scale h around this point. And so the result with Alejandro Rivera says that you can take the limit h to 0, and this family of random fields converges to something depending on t. And then if you take the limit t to infinity, then your random field which will converge to the Berry field. Okay, so you must take the limit h to 0 and then t to infinity, and so somehow it's less precise than Roman's result, but we do get the Berry field. And so if the phase was monochromatic, then you get something which is the monochromatic Berry field. And if the phase is not monochromatic, then you have a Berry field for some measure which is not monochromatic. It's just the push forward of your amplitude squared by the gradient. And so this is somehow the first analog of Berry's conjecture on manifolds of negative curvature, but as I said, it's not for eigenfunctions. It's just for propagated Lagrangian states, and somehow it's not completely satisfactory because we would like to take the limit h to 0 and t to infinity at the same time, and so this is something we are trying to do with my colleague Martin Vogel from Strasbourg University. And unfortunately, we are not able to work directly with all Lagrangian states on manifolds of negative curvature. We need to perturb the operator a little bit to obtain this. So I will say a few words on these results. So we consider a perturbation of the Laplacian, of the semiclassical Laplacian by a random Schrödinger operator. So more precisely, we consider a random Schrödinger operator on our manifold, which is made of a sum of IID random variables times little bomb functions, which are localized at a scale h beta from different points. And beta should be something smaller than 1/2. Okay, they should somehow cover the whole manifolds by little bumps like this, and you give each of them a random weight. So that's what our potentials are like. And our perturbations of the Laplacian are like this. So you have minus h squared Laplacian plus h alpha times your random potential. So alpha is something which is going to be between 0 and 1. So it is a small perturbation of the Laplacian, if you want, in the sense that it's almost something sub-principal, but it's something which oscillates very fast. And so the result, which with Martin Vogel, which is still work in progress, says the following thing. So there exists a choice of alpha and beta. There exists some alpha and beta such that we have the following results. So you start with a Lagrangian state, which is associated with a phase which is monochromatic and which is transverse to the stable directions. Okay, we have no genericity assumption here, and you propagate it during a certain time by the Schrödinger equation, and the time during which you propagate it should be something which goes to infinity with h, and which should be smaller than epsilon log h. And the epsilon is not at all explicit, but it's positive. And then you can say that with a very large probability, the functions you get satisfy Berry's conjecture, meaning that random fields you get from your propagated Lagrangian states will converge in distribution to the Berry field. So here we don't need to take the limit h to 0 and then t to infinity. We are able to take the two limits at the same time, but the price to pay is that it doesn't hold for the Laplacian directly. We need some genericity again, and the genericity is obtained by perturbing the Laplacian by something a random operator, and this result holds with probability 1 minus O of h infinity. Okay, so if there are no questions about the results, I will say a few words about the proof. So,
excuse me, may I ask you a question?
yes, of course.
So do you have counterexample in the case when system is integrable? So when, for instance, on round sphere?
To Berry's conjecture, yes.
Yeah, no, to your theorem, I would say.
Yes, of course. On the round sphere, let me think. Okay, on the simplest example I can think of is on the torus. If you take just one plane wave, it is a Lagrangian state, and it's also an eigenfunction. And if you propagate it, of course, it doesn't move.
Yeah, but you made random choices, kind of, right? So you made generic choices in all the formulations, if I understand correctly.
You mean okay? Sorry.
Yeah.
About the so maybe you're right. Maybe.
Oh no, I didn't make any statement.
No, sorry.
Yeah, I'm sorry.
No, it cannot be. It cannot hold on the. Okay, the thing is that in my theorems there is this assumption of transversality to the stable directions. So on manifolds of negative curvature, this is somehow a generic assumption on Lagrangian submanifolds so on faces. But of course on the sphere, say, there is no transversality to the stable directions, if you want, so you cannot make an assumption like this.
Yeah, but I can just talk about generic kind of Lagrangian state, and then
but I mean, if you have I mean, on the sphere, you could imagine you could imagine Lagrangian states which would evolve in a periodic way, and even if you perturb them a little bit, it would still evolve in a periodic way, quasi-periodic way, I think. So I don't believe you can hope to have a statement like this on the sphere.
Okay, thank you.
Yeah.
Thank you.
But yeah, genericity somehow is going to play a more important role than negative curvature. That's for sure.
I mean, I think maybe I can make a remark on that.
Yes, of course.
Because in the paper where I look at the equidistribution of Lagrangian states, I as well look at integrable systems. And
about that.
Roughly speaking, what you get is that if your Lagrangian is transversal to the foliation into invariant tori, you get, roughly speaking, equidistribution on every torus, and then in kind of average that. But I think, if I remember this correctly, that required some twist condition on the integrable foliation, which I think for the sphere is not fulfilled. So the sphere could actually be an interesting case to look at.
Okay, that's an interesting remark. Thanks. Okay, but yeah, you probably couldn't have something like this for Berry's conjecture, because you know, you're working with semiclassical limits, and so these are objects which are really well defined in phase space, and so you can say that the semiclassical limits you get from your Lagrangian states will decompose in a nice way with respect to this foliation of the dynamics. But here, Berry's conjecture, you're really choosing a point in the base manifold and rescaling around it. You're really not doing something in phase space. You're somehow breaking the phase space invariance. So it's not so clear that you could use integrability in phase space like this. I don't know. I have to think about it. Okay. Thanks for the question and for the remark. Okay, if there are no other questions, I will say just a few words about the proofs, and I will try to be quick, and I will do something which is very dangerous, which is I'll try to prove two theorems at the same time. And so I will just use different colors to okay, so what is in black are ideas which work for both the proof of both theorems. In red, it's something which is used only in the proof of the result with Martin Vogel with a generic potential, and the ideas which are in blue are only for the result with Alejandro. So the first thing you need to do is to understand how to propagate Lagrangian states by the Schrödinger evolution. And so this is done using the WKB method, which is a very standard tool. And so the thing is with the WKB method is that to understand the propagation of Lagrangian states, you first need to understand the classical dynamics and how these Lagrangian manifolds evolve with respect to the geodesic flow. And so what you hope is that the classical evolution of this Lagrangian manifold is still like this. It is still the graph of a function, of the gradient of a function. And it turns out that in negative curvature on the universal cover, this always works, at least when you're transverse to the stable directions. And when you have this, you know that the evolution of your Lagrangian state after time t will still be a Lagrangian state. It will still be of this form up to some small remainder. And the phase you get will just correspond to this gradient you get by evolving the Lagrangian manifolds. And so that is the starting point, and that's what you do on the universal cover. And when you perturb the Laplacian a little bit, what is nice is that to the first order, at least for times which are not too long, what you get is still something like this, so an amplitude times a phase, and the phase is exactly the same, but the amplitude gains a phase. It gains a phase which is there should be no t here, sorry. So the phase you get is related to the integral of the potential with respect all along the geodesic, which you flow to go from here to here. And so somehow this phase you get, it depends on the random potential. So you should think of it as some random phase. So basically, adding some random potential will give you some random phases in the amplitudes. And so this discussion was all about the universal cover. And so then when you really work on your compact manifold, you need to lift things to the universal cover, propagate, and then project back. And what you get is a sum of Lagrangian states like this. So really your propagated Lagrangian states can be written as a sum of Lagrangian states. And then what you want to do is to work locally. We are going to...
Excuse me, why is this sum finite?
That's a good question, because how should I say? Yes, the support of this Bt will correspond to the support of B, which we transport by the classical flow along these directions, gradient of phi. Okay, and so somehow in finite time, you start with something which is compact, and you propagate it during some finite time, and so it will remain in a compact, which does depend on t. But then when you project things back on the base manifold, you only have a finite number of Lagrangian states. So of course, this number grows with time, and it grows exponentially fast with time. Okay, so then I told you that we wanted to do rescalings around points, and so we need to yes. So I will to do rescaling. I will. We'll always be working around a point x0, x1, and I will pretend that I am in RG because I don't want to work with exponential maps all the time. And I will denote by psi the different gradients of the faces. And so for the generic result, what the key lemma is that for generic faces, this you have that these vectors are rationally independent. So I mean for each for all t and all time and almost every x, these directions of propagations, these psi, are rationally independent, and that's the key result of which helps us to prove things for generic Lagrangian states. And so this generic subset is obtained using Thom's transversality lemma, and it's something which is very hard to describe explicitly. It's not at all as explicit as just being transverse to the stable directions. For the blue part of the proof, I will use this rational independence. Okay, so now we want to do rescaling around the point x1, and so when you rescale things around x1, what you get is you can Taylor expand the amplitudes, Taylor expand the phases, and to first order, what you get are just the amplitudes at x1 and the value of the phase at x1 and the exponential IHR minus 1x scalar xi. So basically what you get is just a sum of plane waves. And the only thing which depends on x is here. So yeah, that's a sum of plane waves. And so here we have two different arguments. So for the generic Lagrangian state result, what we say is that here x, we're going to take it uniformly at random in a big ball. And so by ergodicity, since the directions of propagations are rationally independent, this is just ergodicity of the flow by an irrational vector on a torus, and so these plane waves will just converge to how should I say? Yeah, it's just going to converge to the random plane wave, to the plane wave with a random phase and these amplitudes and these directions of propagations. And so then what you need to do is to say that these this measure will behave asymptotically in a Gaussian way. That comes from the thanks to the central limit theorem, it behaves asymptotically as a Gaussian of variance sum of the b of x1 squared. And then you need to use a bit the dynamics and the ergodicity of the geodesic flow to show that this sum of b of x1 squared is going to converge to the L2 mass of b. That means that the L2 mass of B equidistributes over the manifold, if you want. And so these are the key ideas in the proof of the first result. And in the second case, so we don't have the irrationality here. We don't have rationally independent directions of propagations here, but we do have phases here which we should think of as being independent, and that's the main thing which we use. So we must show that these random phases are essentially independent and use the central limit theorem to conclude. Okay, so these are the main ideas of the proof. I'm sorry if I was very fast at the end and maybe not very precise, but I thank you for your attention.
Thanks a lot, Maxime, for the talk. I think we have time for some questions now. So if you have any questions, either unmute yourself or ask them in the chat, please.
Yes, I have a question. When you propagate your Lagrangian state,
yes,
why you don't get some caustics?
That's a good question. So that's because we are in negative curvature, and we suppose that we are transverse to the stable directions.
And it's enough.
And well, you could have caustics in finite time, But if you wait a bit, then everything is going to be fine. And that's why we, I mean, yeah, in the first result, I said that for T large enough, you could have caustics in finite time, but then no, the Lagrangians will just points on the Lagrangians.
Okay.
Get further and further.
I have another question. It's about the fact that the phases are rationally independent.
Yes.
You need no Diophantine condition. It's just independence is enough.
So that's a very good question. Sorry. Here, so yeah, in rational independence is enough to take limits like this: h to 0 first, t to infinity then.
Yeah.
If we wanted to take t to infinity at the same time as h goes to 0, if you wanted to have something more quantitative, to take the two limits at the same time, then we would need some Diophantine condition.
Okay.
But we couldn't hope to have something like log h. I think we convinced ourselves that we could maybe take t to log h, and so that's the first issue. And the genericity is more complicated to describe then. We couldn't have a G delta dense set because Diophantine is not G delta dense. We will need some genericity in the sense of a probability measure on the set of Lagrangian states, and that would be a bit tedious to write down. I mean, it's good for PhD students, but we are too old to do this.
When you said when lambda 1 is equal to lambda 2, you said it's not a nice metric space. What do you mean? It's not a manifold, or because it's still a metric space because it's a subspace of.
Yeah, you're right. But
it's not. It's no more a manifold for me.
Yeah, here you have an open subset of manifold. Here, since you're not an open set, it's, you want to talk about genericity. You want to talk about open dense subsets. If you're not an open set, it could become more complicated.
It's still a complete metric space.
Yes. I mean, we chose to use another way of describing the topology on this, not to use directly, convergence of the gradient and its derivatives, but maybe we could do this. But it's not even clear to me that you don't have isolated space, isolated points in this set. Can you always?
So the problem is that it's no more a submanifold of the previous. That's exactly what you mean, I guess.
Yes.
Okay, thank you. No other questions for the moment.
Okay, thanks.
Thanks for the questions. Do we have any other questions for Maxime?
Yeah, maybe I have one or two. So as well about this point with the genericity. So do you think that there might be Lagrangian submanifolds for which the Berry conjecture does not hold?
No. My conjecture is that in negative curvature, if you start with any Lagrangian state which is transverse to the stable direction, and you wait long enough, then they will all you will get Berry field. I mean, you did get quantum unique ergodicity for these functions. There is no reason not to get Berry's conjecture. But well, the two theorems are presented are just two attempts to prove this.
Well, I mean, very impressive. I mean, a tour de force. It's a very nice result.
Thanks, Roman. There's a question by Lior Alon. You can unmute yourself if you want.
Hi. First of all, thank you very much for the talk. I have a question. I guess it's partially related to the Diophantine question. So I'm trying to figure out where will the Ehrenfest time kick in here, and where would it come from? Would it come from the n of t, the number of summons, the number of you have here you're propagating upstairs and then you're projecting downstairs, and the propagation somehow captures how many linearly independent directions you will have. And this is the number that goes to infinity and gives you the ergodicity. So I'm trying to figure out if this is the propagation upstairs is where you see the Ehrenfest time, and where.
No, actually, we don't see the Ehrenfest time in what we do.
No, you don't have it here, but as you remarked to Yves' question,
Yes,
you said whether it's going to be log or log. There should be some kind of an Ehrenfest type threshold to how you're taking the two limits, the h bar and the t.
You're completely right, but the correct Ehrenfest time is of size log h, a constant times log h, and the fact that we would get a log h or log h or log to the nh, it's just an artifact of our proof. It's because the proof of this result is really very naive. I mean, using irrationality is it's really a very naive phenomenon, and it is not what should I say?
Quantitative.
Yes, and it really isn't the phenomenon which is at the heart of quantum chaos. It's just something we introduced. It worked. We were happy with this, but I mean, it should be possible to have a proof which goes up to log h, and that's what we tried to do with Martin. Even though the result doesn't look that different, the techniques which are behind are much closer than what we really expect to be the key phenomena in quantum chaos, because we have these Lagrangian states which evolve in different parts of the manifolds, and which are going to gain some phases which are independent, and all the independent phases mix up, and you get Gaussian statistics. That's so no, the correct Ehrenfest time should still be something of size log h. That's my belief.
Thank you.
You're welcome.
Thank you, Lior. We now have a question by Amir. If you want to unmute yourself.
Yes. Hi, thank you for the talk. I had just a speculative question about whether or not you expect something like this to be like a version of Berry's conjecture to be true, but also on the boundary, or for example, for restriction of Cauchy data to a hypersurface.
What do you mean on the? You mean for your first question, you mean on a domain with a boundary?
For example, if you have chaotic geodesic flow, but
yes,
with reflections.
But yeah, it should hold.
Not in the interior though, but I mean on the restriction to the boundary.
Very close to the boundary.
Actually on it. So if you look at like Dirichlet boundary conditions, and then you take normal derivative at the boundary, and you look at this Cauchy data there, and can you see any kind of this like universal scaling, but as a function now on the boundary?
I have no idea. I have never thought of it.
Or for some hypersurface which goes through the middle of the node. Yeah. It's kind of like quantum ergodic restriction theorems or something.
So you need some extra assumptions to have this, I guess, because imagine that on your manifold of negative curvature you have an axis of symmetry, something like this. Then of course your eigenfunctions will not have fancy statistics on this axis. Yeah, maybe for along generic submanifolds of the hypersurface, it should be true. Yes, indeed. But I think our methods of proof should give this.
I see.
Yes, I'm quite confident about this. We didn't address this question, but okay. Thanks for the remark. It's very good.
Thank you.
Good remark.
Thank you very much, Amir. Do we have other questions for Maxime?
You
Go
promised you had no more.
Okay, no, but I was thinking to another question. Can you say something if you, instead of looking at Schrödinger propagation, you look at wave propagation?
I believe that things should work more or less the same. I mean, you do still have WKB method, which works for this.
Mhm.
So yes, I didn't. So for the work with Alejandro, I'm quite confident. For the work with Martin, I'm a bit less sure, because the key of the results is that you do gain these small phases. I didn't do the computation for the wave equations. I mean,
Okay.
it already took me some time to convince myself that it did work this way for Schrödinger propagators. And you need to convince me that it works like this for the wave equation. No, probably it should work.
Thanks a lot, Yves, for the other question. I think we can thank Maxime again for this presentation. Next week, we will not have a presentation, as many of us will be at the same conference on the next week. So we will restart in 2 weeks with a talk by Semyon Dyatlov on the Ruel zeta 0 for nearly hyperbolic 3 manifolds. In the meantime, thank you very much for being here today, and see you in 2 weeks.